Welcome back to ECE 441A, 541A on this chilly morning. Not really, it's November 2nd and we're still enjoying beautiful weather. But homework number 6 is due on Monday. Next Friday is Veterans Day and the university will not be holding classes, or at least I've been told not to have classes. So that's a week from Friday. We will not have class. Stay tuned as to whether you will get provided with makeup or additional material because we're missing so many days. I know that you don't want to be missing out on that much material. Homework 7 is planned for the 16th, which is a Wednesday, and that's the period before our next exam, which is a week after Veterans Day. Our next third exam will be dealing with the root locus, construction, and design, and the exam is structured a little differently this time. I know that you liked having 5 problems, so it will probably have 9 problems. Look at the exam practice material on D2L. I may make that available shortly after we've had a few more construction rules. The lab number 3 is due on the last day of class. That's upon us before we know it, the 7th of December. And project, if you're in 541A, there's 2 different dates for deliverables. The first deliverable, which is really your proposal on the project, is due on the 21st of November, and the main part of the project, which is deliverable number 2, is due on the 7th. The third deliverable is your reflective paragraph on what you did, what you learned, what you wished would have happened, etc. Today we have one goal, but that involves many different rules. So we are going to continue with looking at root locus construction rules, and in particular, we will see if we can get through all 6. I'm not banking on that happening, but we will start with rule number 3 and continue progressing from there. Again, as I said last time, these root locus construction rules, you may not have all of them applied all of the time, but I've tried to add in a few more details this time in the, let's say, bulleted list of 6 rules. And what you will need to do is just get comfortable with looking at those and being guided by those rules as to what you need to perform or do in sketching these root loci. That's the idea behind these. The starting rule is really not hardly a rule. It's just putting X's and O's on the S-plane. The next one is the cutting of the bread and finding the segments of the real axis that are apart or belong to the root locus. And with negative feedback, that's a negative or an odd number of poles or zeros to the right of that segment. We will start today with rule number 3, which is the asymptotic behavior for large K, and that asymptotic behavior is interesting when we have a pole zero excess more than 1. A pole zero excess of 1, we have an asymptote at minus 180, and so our root locus is going off to minus infinity, one of the branches. When we have more than that in terms of our pole zero excess, and that's the P minus C in the denominator of those 2 formulas, then we have more interesting angles. But you're essentially dividing 180 degrees by the pole zero excess to obtain your fundamental angle, and that's the one that you can key off of. Meaning if you have a pole zero excess of 2 more poles than zeros, then your fundamental angle is 180 divided by 2, or 90 degrees. If you have a pole zero excess of 3, your fundamental angle will be 180 divided by 3, or 60 degrees. And we'll see how those start to present themselves as we move through rule number 3. Rule number 4 may or may not occur. It occurs when poles or branches approach each other on the root locus or move away from each other on the real axis. I say the root locus on the real axis when they break away. If we have 2 poles coming together, they are going to meet and break away. They do that at a relative maximum of k. We crank up the k, and we're getting bigger and bigger from the right and left. Right at the maximum is when they depart. If they come back into the real line, then that's a relative minimum, because as you crank up gain k, they start to move away from each other. So the breakaway and reentry points are at these relative mins and max of the gain k, and that will all be determined from this magnitude condition of the magnitude of kgh is equal to 1. The imaginary axis crossing, if we do have root locus branches going across the imaginary axis, we can find those points because they should satisfy the phase angle condition if it's on the root locus, and we can use that to determine. And the angles of arrival and departure, again, we will use the phase angle condition to find if we do have complex poles or complex zeros, how do our root locus branches depart from those poles and arrive onto those complex zeros? And we're interested in the angle at which that happens. So it's a departure angle or an arrival angle. And it may not even happen. If we have no complex poles or zeros, we don't have to worry about rule number 6. So the imaginary axis crossing is a point on the imaginary line. That's rule 5. But the angle of arrival and departure happens when we have complex poles or zeros anywhere in the complex S-plane. Then the root locus branches will depart from the poles at some angle, or they will arrive at the complex zeros at some angle, and that will make more sense as we get into rule number 6. Here's where we left off last time, and I'm simply restating the rule, maybe a little bit more formally or with a little bit more information, but the root locus is asymptotic to straight lines with particular angles. And those angles are determined by the fundamental angle that then gets incremented in odd multiples. Meaning if we had one 90 degree, then we go 3, that's 270. So I'll just say plus and minus 90 degrees because 270 is the same as minus 90. That's when we have a pole zero excess of 2. If we had a pole zero excess of 3, then we have 60 degrees. 3 of those, 180. 5 of those, 5 times 60 is 300. We're now at 300. So we have 60, 180, and 300 for our asymptote angles. And where those asymptote angles are centered at a point on the real axis is determined by summing up the poles in G of S, H of S, subtracting the sum of the zeros of G of S, H of S, and those are the finite zeros, divided by the pole zero excess. Let's now do that, or look at that, with our example from before, or one of our examples. This was example 2. Example 1 really had sort of a trivial asymptotic behavior because it was going off at minus 180 degrees. In this G of S, let's say that H of S is 1. How do we get started on our root locus plot? Let's go ahead and quickly work through all of the different rules. How do we begin? Pardon? So now we want the X's and O's, don't we? And the denominator is going to get the values of S that make the denominator vanish will be our X's. Those are at minus 4, minus 6, and minus 10. And we have 1 0, finite 0 at minus 1. That's rule 1. Rule 2 tells us which of these segments of the real line belong on the root locus. And we have several segments that we've cut the real line into, one between minus 1 and plus infinity. That doesn't belong to the root locus. This piece does because we have an odd number of poles and zeros to the right of any point in that on that segment. The segment between -4 and -6 is not on the root locus. The segment between -6 and -10 does belong on the root locus. And now you can see that as we increase the gain k, and the branch or the pole, the closed loop pole, this red line tells us where all the possible closed loop poles could live as we had for particular values of gain k. As we crank up the gain k, the pole at -6 goes left, and the closed loop pole at -10 goes to the right. Those are going to meet. And now we need to find in Rule 4 where they break away, but let's first find Rule 3, which is where they go at high values of gain k. So you could do these rules in different orders. We could now start with start doing Rule 4, but let's go ahead with Rule 3, which is the asymptotic behavior of the root locus or the branches. And Rule 3 hinges on the pole zero excess. We have 3 poles, 1, 0. Our pole zero excess is 2. The asymptote angles now, the fundamental angle is 180 divided by that pole zero excess, P minus C. And then we will look at the number of multiples we have depending on L, and L advances from 0 to 1, which is P minus C minus 1. Or, what are the angles of our asymptotes for these 2 branches? Those are the zeros at infinity. We have 2 zeros at infinity. What are the angles of those branches? We have 90 degrees and 270, which I'm going to usually just say plus and minus 90. But here, if you simply work down the angle formula, you would have 90 degrees, which I will typically just say, oh, our asymptotes are at plus and minus 90 degrees. Now, we have some asymptotes, one going off at 90, one at minus 90. We need to know where do we pin those 2 asymptotes on the real line. So now you can think we're in a party game and we're pinning the tail on the donkey. But now we're pinning the asymptotes on the on the real axis. You're not going to forget this, right? You now are pinning this set of asymptotes on the real line or the root locus, and they will be pinned based on the centroid formula, which is we now sum up all of our poles. We have a pole at -4, a pole at -6, and a pole at -10. We sum those up. Then we subtract from those our zeros. And really, it's the real part of the zeros. The imaginary parts, because they are going to come in complex conjugate pairs, are going to cancel. In this case, we have a 0 at -1, and we divide that number by the pole zero excess, which is 2. In this case, we have -20 plus 1, or -19, divided by 2, or the asymptotes are now centered at -9.5. Meaning we now come here and we say there's 9.5. Our asymptotes now are at plus 90 and minus 90. And we know that eventually the branches of our root locus are going to approach those asymptotes. What we don't know is how they get to those asymptotes exactly. And that's going to depend on where the pole at -6, or that starts at -6, and the pole that starts at -10, where they break away from that segment of the real line. And that's our breakaway point. How many branches do we have? We have 3 branches. And initially, we just have 2 real axis segments, don't we? But one of those real axis segments possesses or contains 2 branches of our root locus. Let's now find where the pole that starts at -6 and the pole that starts at -10, where they break away from the real line. And that's going to be then rule number 4. Yes? L equals 0 and 1. This is now we simply increment, so the question was where did L come from, or where are these values? L is just the index of how many multiples of this fundamental angle do we have. And that just starts at 0 and then it just keeps going until we reach P minus C minus 1. And in this case, P minus C was 2, so we just needed to find L equals 0 and 1. As our pole zero excess increases, we obviously are going to have more asymptotes going off in different directions. Question? The centroid of minus 9.5 is where we now center those 2 asymptotes. We have one asymptote at 90 degrees, another one at minus 90. We now need to know where do we pin that on the real axis. And that's now pinned for this example at minus 9.5. So this was, maybe I should label that. This is now sigma sub A equal minus 9.5. Is that better? So that's where the asymptotes are centered. And that's why we call it the centroid. Now what we want to do is look at where the poles that begin at minus 6 and minus 10, where they actually meet and break away from the real axis. And we know that they are going to break away somewhere between minus 6 and minus 10. If those were the only 2 poles, if we had nothing else in our pole zero diagram, they would meet exactly in the middle at minus 9. No, sorry. What's the midpoint of minus 6 and minus 10? Just seeing if you guys are awake. I'm obviously not. It's minus 8, isn't it? So it will go right to minus 8 and break away. If you were in a rush on the exam, you could just say, well, we know it's close to minus 8. I don't have time to calculate rule number 4. And that would give you a half of a point out of 20 or something. Hopefully you heard the laughter if you're listening to this recording. But that was meant a little bit of a joke. But let's now see how close to minus 8 it actually is, because the pole and 0 at minus 1 and minus 4 are influencing where those 2 poles will meet between minus 6 and minus 10. And that's where rule number 4 comes in, and that's the breakaway and reentry. And we may have a breakaway, we may not have a reentry. We may have a reentry and we may not have a breakaway. It depends on the collection of poles and zeros that we're dealing with. But this happens on the real axis. And the breakaway and reentry point does not have to necessarily be in, how do I want to say this, where our root locus segments might be located. It might be outside of that. But here, let's now say a little bit more. The breakaway, and then in parentheses, I'm going to say reentry points occur at relative. For the breakaway, we just crank up the gain, keep cranking up the gain, and when they meet, that's a relative max. So the breakaway is at a relative maximum. The reentry, now they come in, and as you crank up the gain k, the k gets bigger along the s-axis at that. And so this is now at a relative minimum for the reentry. And the way that we will find this relative min and relative max of our gain k is by using the magnitude condition. And as I said when we started this discussion of the root locus, all of our rules hinge on two conditions, either the phase angle condition or the magnitude condition. Here, we are using the magnitude of k, g of s, h of s, equaling 1. And in our example, we had k times s plus 1. That was, our g was s plus 1 over s plus 4, s plus 6, s plus 10. And we want that magnitude, or that magnitude has to equal 1. And we can now solve this for k. And typically we're looking at positive values of k from 0 to positive infinity. If we factor out the k and push everything else on the other side, and realize that the magnitude of a product is the same as the product of magnitudes, we can write this as the magnitude of the s plus 4 factor times the magnitude of the s plus 6 factor times the magnitude of the s plus 10 factor all over the magnitude of the s plus 1 factor. Are we okay with that? And what you will actually see if you now performed that maximization or minimization problem, if you took the derivative of this and set it equal to 0, you would find that this k is maximum at a value of s equal to minus 8.202, and the k value that is maximized at that value is 2.31. Pardon? Which is close to the minus 8, which was halfway between. How do you find that? Well, you can find this many different ways. If we simply put up or created sort of a graph or a chart, and we said, what is k when s is equal to minus 6? If I now plug in s equal to minus 6 into that formula for k, what do I have? What's that middle factor going to give me if I substitute minus 6 in? 0. So k is 0, and that's consistent with what we know. K is 0 at our open loop poles. What about if we said, okay, how big is k at minus 7? Well, then you could punch it into your calculator, right? Quickly. Oh, come on now. You can do this without a calculator. You have 3 and 1 and 3, right? 9, and you can get minus 8.202 on your calculator. If you get a tenth of a digit, that's fine. So now let's look at what we get here. You guys are giving me the business. This is now 9 divided by 6, right? We had 3 times 1 times 3 up top divided by 6 downstairs by substituting in minus 7 for s into this k formula. Stick with me. What? There's 9 problems, and you have to do this 10 different times. You guys. Now, what happens if you plug in at minus 8? Now you have 4, 2, and 2. Right? What did I have? 16 divided by 7. So this is now 16 over 7. And maybe you don't see it going up or down. It's increasing, isn't it? It was a little bit. 9 over 6 is 1.5. Yes? Keep me awake. And now 16 over 7 is above 2. Is it not? Then we can go to minus 9. I'm not even listening.
Me neither.
We have, and you guys need to listen, but I'm not. We have minus 9, and you can do the calculation, and you obtain 15 over 8. So now what do you see? Between minus 8 and minus 9, you've hit a maximum, and you've come back down. So now you can narrow your search. You guys learned all these algorithms in all your classes, right? Now we have a search algorithm. Now you could say, let me check minus 8.5. Or if you have another calculator, you could actually sketch this. You could graph k as a function. You could graph k. There's many different options. I'm just giving you this. But now do you understand how to find k? We did it numerically. Now you can see that k varies as a function of s. And you want to see how does k vary between minus 6 and minus 10, and you're trying to find the maximum. So if you plotted this, let's say that we now check the points. I said I'm not listening. If we check the points between minus 6 and s equal minus 10, this will probably make the wildcat. Yes, was there a question? It's too late now. So now what does this behavior? You now have this cubic divided by a linear. So what does the shape of this look like if you actually plotted this relative to the values of s? Here is s. You would find that you now, and I'm not going to sketch this very accurately probably, but it will do something like that. And this peak is obviously happening at minus 8.2, and the value of gain k over here, this we found, if we substituted minus 8.2 into that formula, we would find a k of 2.31. So now you're having one maximum between minus 6 and minus 10. Where's my plot? So now what do? At this point, we can go to minus 8.2, and we now know that we break away at that point and approach our asymptotes. And that's basically the completion of our root locus sketch for that particular pole zero pattern. We've now finished, and we don't have to do rules 5 and rule 6, which was the imaginary axis crossing and the angles of arrival and departure for this particular pattern of poles and zeros. So the S values here, where do you expect, if you were to look at this root locus, where would you expect a breakaway? Between minus 6 and minus 10. You have two branches, they're coming together. You now know to investigate the value of k between minus 6 and minus 10. Hopefully in that interval you have one relative max, and we showed that with the plot. You could also pull out your calculator and plug in k is equal to the absolute value of x plus 4, x plus 6, x plus 10 divided by x plus 1, and just plug in different values for x. Say with x equal minus 8, with x equal minus 8.5, and you can sketch this. Or you can plot it if you have a graphing calculator. You could just plot that particular expression. We're finished with that particular problem. Are there questions? Do you see what rules we had to do? We used rule 1, that put down our poles and zeros. Rule 2 found the segments of the real line that were a part or belonged to the root locus. Then we said, oh, we have two more poles than we have zeros. We have asymptotes at plus and minus 90 degrees. We found where those asymptotes were centered at minus 9.5. Then we said, where do we break away from the real line between minus 6 and minus 10? And we found that to be minus 8.2. And boom, we're done with our sketch. On to the second problem. Yes? So it's just the poles that are migrating. The zero is attracting these poles. And we have finite zeros and we have infinite zeros. And those asymptotes are telling us where our infinite zeros are located. And that's why it's not going to break away between -4 and -1. If you evaluated k between -4 and -1, you would just see k monotonically increasing. You wouldn't see a relative max or a relative min. And that's important if we did have something happening between some or on some branches. We might actually have at some point reentry and breakaway. And so there we would look for a relative min and a relative max in that region. And that would tell us, oh, we do have some interesting behavior going on between those 2 points or on that branch. Let's look at some more interesting features which arise from rule number 5. I don't even have my glasses on, so I'm neither seeing nor hearing from the audience at this point. And the entire class is playing together with me, right? They've put their heads down on the desk and earphones, earbuds in. We've completely lost this class. We've reached an imaginary point. We're talking about imaginary axis crossing now, okay? In the last example, that didn't happen. We had no branches crossing the imaginary axis, so we wouldn't even play this rule. We wouldn't have to use this particular rule. But this rule now deals with branches of the root locus cross the imaginary axis if the phase angle condition is satisfied at that point. If you thought the iteration process was involved last time, what do you think about looking at an infinite number of points on the imaginary axis and checking your phase? Okay, I'm getting carried away, but that's sort of what you're looking at doing now. You could evaluate on the imaginary axis the phase angle from those poles and zeros, and when it became equal to -180, that would be the point where your root locus would be crossing the imaginary axis. Let's look at an example of this before you get completely asleep. And we obviously have to put in a new system because our last system didn't have this happening. Here, let's say that we now have an S plus 3, and an S plus 6. And if we sketch the root locus, we have 3 poles. One at the origin, one at -3, and one at -6. That's rule number 1. Question. So H must be 1 in this case. I'm not giving you an H of S, or if I'm not giving it to you, I'm just assuming we have 1 in the feedback path. Now, how many real axis segments do we have? How many pieces of French bread did we cut our loaf into for this particular pole pattern, pole zero pattern? And now you can fit those pieces on your fingers, can't you? One hand, I hope. We have 4 different segments. Which segments belong to the root locus? We have that segment, and we have this infinitely long segment. And where would you expect a breakaway to occur? You have a branch of one of the poles that begins at 0 and going left. Another branch begins at -3 and it goes right. Those two you would expect to meet. And now we want to know, where do they go after they break away? And that's rule number 3. Do we have the opportunity to use rule number 3, and what does rule number 3 tell us? Rule number 3 will give us the asymptote angles, which the fundamental angle is now 180 degrees divided by the pole 0 excess. That now gets multiplied by 2L plus 1. And in this case, P minus C minus 1 is 3 minus 0 minus 1, or now we need to iterate up to 2. Go from L equals 0, 1, and 2. So we have 3 asymptote angles. And what are those angles? The fundamental is 60 degrees. And if we increment that in odd multiples, we now have 180 degrees, and 5 of those 60s will give us 300 degrees. This is what we had for L equals 0, this is L equal 1, and this is L equal 2. And those are now our asymptote angles. We have an angle at 60, 180, and 300. And now we need to know, where do we center those angles on the real line? And our centroid formula says we add up all of our we add up all of our poles. We had a pole at 0, we had a pole at -3, and we had a pole at -6. And we subtract all of our zeros. We didn't have any. And we divide by poles minus zeros, our pole 0 excess. In this case, the centroid is actually right on top of one of the poles. Don't assume that that's always going to be the case. That's not necessarily going to happen. That's just because of the way I picked these poles. They're very symmetrical, 0, -3, and -6. Now I can sketch my asymptotes. And now, you laughed when I said you can bring a protractor. Now you may want to have a protractor for your exam. You have plenty of time to do the 9 problems if you have a protractor, dividers, your ruler. But now we go up at 60 degrees. Maybe that's not quite 60. Should have brought a protractor. I have another one that goes off at -180, and another one that goes down at -60. Which is 360 minus 60, or 300. This is where, oh, that's a pretty bad 60, isn't it? Let me clean that up a little bit. Now what do we do? Now we can find, where do we break away between 0 and -3. This is rule number 4. So rule number 4 is our relative, is it a relative max or a relative min? We're cranking up K from 0, getting bigger, 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 bigger until we hit, right? So that's got to be a relative max. This is now going to be a relative max between S equals 0 and S equal -3. And it's all coming from the magnitude condition. And in our case, that's K over, or the magnitude of K over S, S plus 3, S plus 6. And since we don't have any poles, or any zeros, Now this is just the magnitude of s times the magnitude of s plus 3 times the magnitude of s plus 6. And you laugh at me, but this isn't that hard to create, this little chart. So at 0, what's k? In that formula, if I plug in 0, what is k? 0. If I plugged in minus 3, what is k? 0. So we know we're starting at those points. What about minus 1? 10. Minus 2? 8. In this case, we could actually say, oh, k is s cubed plus 9s squared plus 18s. And we could, this one's easy because it's just a polynomial. It's not a ratio of polynomials. We can differentiate this. We now have 3s squared plus 18s plus 18. And we can set that equal to 0. We can divide by 3. That doesn't influence anything. And we now have s squared plus 6s plus 6 equaling 0. And we can solve that with our quadratic formula, and we find s is equal to minus 1.3 and minus 4.7. Uh-oh, we have 2. What happened? Which one should it be? Minus 1.3. It has to be between 0 and minus 3 for this particular problem. This is now our relative max. So we now know that if we, and what could we say? We could now calculate that. We could say, let's calculate what k is at that particular value of s. And now we know that we're at a gain of 10.4 to get us to that particular point. Question? What did I use this table for? I was just showing you how you could do it. But now you know that you've gone from, let's say, 0 to minus 1 up to 10, and now you're at minus 2 back to minus 8. So you know your relative max is between 0 and minus 2. And we now found that it was, by doing it analytically, we found a value of minus 1.3. You can do it analytically, but in some cases, if you have a fifth order divided by a second order, you may not want to differentiate. So you may want to plot it. You may want to just do a chart and numerically find within a few guesses a reasonable value for your breakaway. Question? Where's the minus at? I'm not understanding. So now what I'm doing, so now my k was an absolute value, so I could say something like this, and I now want to just find the absolute value of k, or I'm finding relative mins and maxes on k, and then I could take the absolute value of that after the fact, if I wanted to. And so I did in this particular case. I just found, where do I have a relative max or min for this polynomial in S relative to S, and that was at minus 1.3 and minus 4.7. I could discard the minus 4.7 because I'm interested in the breakaway between 0 and minus 3. And then I could evaluate what my k is at that particular point, and now I could ask you all sorts of questions. I could say, find the value of gain k. Maybe somebody has this system and they actually want to locate a closed loop pole at minus 1. Do you now know how to find the gain k to get you to minus 1? Where was our breakaway? At what value of s? Minus 1.3. And what was our k value at that point? 10.4. So we know we don't have to crank it up quite to 10.4 to get to that s equal minus 1. So if we want to find, this would be a design question, find the gain K to yield or produce a closed loop pole, because the red line tells us, or the root locus tells us, where all of our possible closed loop poles could live. And if we pick a point, then we have to find the K to get us to that point. In this case, we picked a point at s equal minus 1. And now we could just evaluate that expression for K when s is equal to minus 1. And we have 1 times 2, so we have 2 times 5. Our gain K to get us one closed loop pole at minus 1 is a gain value of 10. So now we have a relative max at minus 1.3. That's our breakaway. And what we're interested in now is where do those branches, we know 1 is going off to minus infinity. So with a gain K of 10, we know one pole is right there at minus 1. Where's the other one? How many more poles do we have when we pick a gain K of 10? How many closed loop poles are we going to have? How many open loop poles do we have? All right, you were really playing now, along with the game of not listening and not speaking. We now have a pole at minus 1. The other one is to the left of minus 1.3, is it not? Because it hasn't yet reached a gain of 10.4. So it's over here somewhere. You could just guess. That's where I think you get a little bit nervous. You go, where is it? Well, that's not, who knows if that's exact. But then we have another one over here. We should have 3 boxes. If we fix the gain at 10, then we have 3 closed loop poles, and we know 1 is guaranteed to be at s equal minus 1. The other one is somewhere probably between minus 2 and minus 1.3, and the other one is to the left of minus 6. If we crank the gain up even more, we are eventually going to approach those asymptotes. And this is what we are trying to find now. We are trying to find this imaginary axis crossing. That's what we're trying to find next in rule number 5. And what do we know about any of these points that are on the root locus? What do they have to satisfy? They have to satisfy the phase angle condition, and now we could go up the imaginary axis and compute the angle. What's the angle, let's say, to this point from this pole at the origin? What's the angle from the pole at the origin to that green dot? How do you have to rotate relative to the positive real line to face that green dot if you're sitting right there at the origin? You have to turn 90 degrees. So that pole contributes 90 degrees, and it's downstairs, so that will be minus 90. What about this pole at minus 3? What's its angle? Well, if I've sketched my asymptotes right, you know it's less than 60 degrees. And you could do it. You could say, oh, it's the inverse tangent of, let's say, 5 divided by 3. And that's the angle of that pole. Are you seeing this? Not at all? So this angle, did you see? That was 90 degrees. This angle is right there. And this angle is that angle. So this would be, let's say, theta 0. This angle we could say is theta of minus 3, and this is theta of minus 6. The sums of all of those, these angles are all due to poles, so they're in the denominator. So in our phase angle condition, we would be subtracting 90, we would be adding minus 90, minus, let's say, 50, and minus 40. And now, if those are equal to minus 180, we know that green dot is on the root locus. Do you see how I could slide that green dot up and down and those angles would change? And I'm looking for the sweet spot. I'm trying to find when that green dot is right at the point where these three poles produce an angle of minus 180 in combination. That's the imaginary axis crossing rule, and we'll pick up at that point on Friday.